Uh, my dear students, I welcome you to this video lecture on HVDC power transmission systems. As you remember, before the lockdown, we had one lecture on this course in electrical engineering ethic, and it has been about more than 1.5 months that we have been disconnected from each other. So now we have an opportunity. Uh, this is the right time when we have to use the technology for utilizing our time and disseminating the knowledge. Well, on this side it is the source, and on the other side it is the what I should call it sink. I will try to uh, discuss various aspects of this technology with you, and let us take a pledge that we will make the best utilization of the time with us. The idea is to seek knowledge in these very tough times. Why to only eat and sleep, do nothing? This is the time when we have to do something positive, which will differentiate us from animals. During these tough times, we have to, if you go and seek the knowledge, nothing like that. So, without talking much about other aspects, let's come straight to the topic. In the very first lecture which we had in the electrical engineering ethic, I discussed with you the historic background of HVDC power transmission system. We have seen, and I hope you remember that the first power system was DC power system, designed and developed by Thomas Alva Edison. Then came the age of AC power system. Then there was a war between AC current and DC current. Actually, it was not war between the currents; it was the war between the creators of these currents, the Tesla and Thomas Alva Edison, and ultimately it was the victory of AC power transmission, AC power generation, and utilization over DC for various reasons which we have discussed inside the class. Now, for many years, it went like this. The electrical power generation was AC in nature, the transmission was AC in nature, the distribution was AC in nature, and finally the load utilization, the utilization of power in the load, it was again AC. Although many loads internally have rectifiers, they convert this AC into DC, but the power which comes to our homes, it's AC in nature. And then, we convert it into DC in various equipments. After a long time, it was felt that as far as the transmission part of this electrical power is concerned, let us have DC power transmission, because DC power transmission at high voltage and over very long distances certainly has the advantages, significant advantages over AC power transmission over long distances at high voltage. Why HVDC? I will write here why HVDC transmission. Why? If power generation is AC, transmission was also earlier AC, why have we shifted from AC power generation to DC power generation? It's a $1 million question. For justifying the transmission of power through DC at high voltages, we have to know what are the advantages of transmitting power at high voltages, high DC voltages over high AC voltages. So we are going to discuss that. Advantages of HVDC transmission. What are the advantages of HVDC transmission? So first advantage of HVDC transmission over AC transmission is there is no stability issue. So you can note down that there is no stability issue. Most of you must be aware of what stability of a power system means. Generally, it is taught in the final year power systems course in our institute. For our BTech students, we teach it in Power Systems 3, the third course on power systems, stability issue. The stability, we know that, for example, if you have a two-machine model of a power system, the power transmitted over a transmission line, it is given by this equation. P is equal to V into V1 into V2 by X sine delta. Or if we assume that the receiving end voltage or the other end voltage is same as the sending end voltage, then the equation gets modified to V square by X sine delta. What is this delta? Delta is power angle, or it's also called transmission angle. We have studied the significance of this delta in the other course in MTech first semester, which was your elective course, Flexible AC Transmission Systems, facts. Now, if you draw the power angle characteristics, the characteristics will look like this. This is pi by 2, and this is pi. And this is the maximum power, P max, which is transmitted over the line. And we know that P max occurs at delta is equal to 90 degrees. And in that case, it is equal to V square by X. This is the maximum power that can be transmitted over a given power transmission line. Now, the problem is that we never operate our system at delta equal to 90 degrees for the stability reasons. Because, I have already discussed with you in details, and you must have also learned in your power systems course that if you operate your system at delta equal to 90 degrees or delta very close to 90 degrees, then stability issues are there. A small disturbance in the system will render your system unstable. Okay, a small fault which lasts for a few seconds, it will make your system unstable. So therefore, the permissible value of delta, the operating value of delta is generally 25 to 30 degrees or 20 to 30 degrees generally. We operate our transmission system at delta equal to 20 to 30 degrees, or you can say 25 to 30 degrees. This is the optimum value. Another problem is that if you want to transmit power over very long distances, as the distance increases, the length of the line increases, this X parameter increases. And with increase in the X, we know that power transmitted is inversely proportional to X. This P decreases. The power transmitting capability of the transmission line decreases. That means if, for example, in first case, let us suppose that we have a 500 kilometer long transmission line and we are transmitting 100 megawatts of power, and the reactance of line is X1. Now, if we extend the length of the line from 500 kilometers to say 800 kilometers, we add 300 kilometers more, the reactance will increase. Now, it will increase from X1 to X2. Now, therefore, the line will not have the capability of transmitting such a large power. So, as X increases, P decreases. And again, there will be stability issues, which means that a power transmission line which has the capability of transmitting a certain amount of power, we are not able to fully utilize it. We operate it at a very low value of delta, say 20 to 30 degrees, and therefore we are not fully utilizing the capacity of the line. The line has capability of transmitting more power, but because of the stability issues, we are not able to operate the system at delta equal to 90 degrees, and therefore the line remains underutilized in a way. This problem does not exist if instead of transmitting the power over AC lines, we transmit the power over high voltage DC lines. Because in HVDC lines, this X term is not there and stability issue is not there. So therefore, in HVDC transmission system, there is no stability issue, and you can have a very long transmission line. The length of the line or the distance through which you transmit the power, it does not, reduce the power transmission capability of the line. You can have very long transmission line, and you can transmit the power over very long, because X, this reactance in DC does not exist. X parameter is absent. So therefore you can transmit power over very long distances, and distance is not, or the length of line is not the constraint. And another point is that since stability issue is not there, you can load the line up to its thermal limit. What does thermal limit mean? जब तक line जल न जाए, because when you transmit the power over the line, there are I square R losses. And temperature, because of these I square R losses, the line can heat up, and you can keep on increasing the transmission of power over this DC line until it burns. We will never, of course, do that, which means that we can load the line fully up to its thermal limit. And it is not possible to load an AC transmission line up to its thermal limit because of the stability constraint, stability issue. So therefore, the first and the foremost point, a very important point and a very important advantage which an HVDC power transmission system offers over AC power transmission system is that there is no stability issue in HVDC power transmission. We can transmit bulk amount of power over a DC transmission line over very long distances at very high voltages. Stability is not an issue, distance is not an issue, of course. So this is the first point which goes in favor of HVDC transmission. This is first advantage. This is my duster. What is the second advantage of transmitting power over DC, over AC? Second advantage: no reactive power compensation is required. No reactive power compensation is required in DC transmission. See, if you are transmitting power over AC, the AC line has got reactance, okay, and you need to compensate, and then there is the flow of reactive power over AC transmission line. Let's forget about line reactance. Load demands the reactive power. This reactive power flows over the line, and you have to compensate for this reactive power for improving the stability of the system, for damping the power oscillations, and for providing the voltage support and all that. Those of you who have done that facts course with me in MTech first semester already discussed these points with them in details. It was very useful discussion at that time. So therefore, you need the reactive power compensators. The simple compensator is a bank of capacitors, shunt connected capacitors. And nowadays we don't use shunt connected capacitors. We use various FACTS devices, like we use SVC, static var compensator, or we use STATCOM, static synchronous compensator, STATCOM. What is the function of these shunt compensators? They compensate for the reactive power which is flowing over the line, which causes the voltage drops, large voltage drop over the line, which causes very poor voltage regulation over the other end, that's load side end, and which makes your system unstable after certain amount of power flow over it, and which causes power swings, power oscillations in the transmission line. To overcome all those problems, you provide this reactive power compensation through shunt compensators, the simplest being shunt capacitors. We don't need this compensation if we are transmitting the power over DC line rather than AC line, because in DC there is no concept of reactive power. You have a DC transmission line, DC power is flowing over, only active power is flowing over it. There is no reactive power concept in DC transmission line. So therefore you don't need the reactive power compensation, shunt compensation. You don't need to connect a STATCOM, you don't need to connect an SVC, you don't need to connect a thyristor control series capacitor and all that for reactive power compensation. There is, because in DC there is no reactive power, right? So therefore this reactive power compensation is not required if you are transmitting DC power, and if you are not transmitting power over AC lines, you are transmitting power over DC lines. So this is the second advantage offered by HVDC power transmission over AC power transmission. What is the third advantage? No reactive power loss. No reactive power loss. I hope all of you know the difference between reactive power demanded by the load and reactive power loss. The reactive power which is flowing in the system is actually the reactive power which is demanded by the load, and most of the load which is connected to a power system is a reactive type of load. It may be induction motors, large induction motors in industries, or it may be domestic type load, it may be commercial type load, it may be agricultural type of load. Almost all of this load is reactive in nature. So therefore this load demands the reactive power. Okay, this reactive power has to flow over the transmission line. And then there is reactive power loss because the transmission line has its own inductance, reactance, X. This is the reactance of transmission line. And when current flows through this transmission line, just like you have active power loss, I square R, similarly you have reactive power loss, I square X. It is the power, reactive power, which is not because of the load, which is because of the line reactance, and it is called reactive power loss. Do we have any reactive power loss in DC transmission lines? Answer is no, because when we are transmitting power over DC transmission lines at high voltages, in DC there is no concept of reactance. DC transmission line will have resistance only, it will not have reactance. So therefore there is no reactive power loss in HVDC transmission system. So therefore we are overcoming this problem also. Actually this reactive power loss is responsible for voltage drops. Okay, this reactive power loss is unlike active power loss. It does not cause any heat dissipation because it's not active power which is actually being wasted there, which is actually being dissipated there. It is the reactive power loss. It is the reactive power because of the reactance of the transmission line, long transmission line, and it is responsible for large voltage drops across the line, so that your receiving end voltage always is less than sending end voltage, and it deteriorates the voltage regulation. It makes voltage regulation very poor. So therefore in HVDC transmission systems we don't have any line reactance, so there is no reactive power loss. I hope you have understood. What is the other advantage of HVDC power transmission over AC power transmission? Other advantage is that power flow control is possible. Power flow control. It is possible to exercise control over the flow of power over parallel transmission lines. Those of you who have attended my facts classes in first semester of your MTech course, we have discussed it in very details, long details. What does this mean? I will just discuss it partly with you. So this is our transmission system, an interconnected transmission system. Suppose we have three parallel transmission lines, and these transmission lines have the reactances X1, X2, and X3. The power transmitted over a particular transmission line is inversely proportional to its impedance. Now the line reactances or line impedances will decide how much power a particular transmission line has to carry. Let us suppose the total load power is P1 plus P2 plus P3, where P1 is the power carried by first line, P2 is the power carried by second line, and P3 is the power carried by third line. So therefore, we would like that these the power P1 should be equal to P2, should be equal to P3. I mean, these transmission lines, these parallel lines, they should equally share the power, but that is not the case. The power which is flowing over a particular transmission line, it is inversely proportional to impedance of the line. So therefore in this case, the line which has higher reactance or higher impedance will be the line sharing less amount of power or carrying less amount of power. Therefore it can remain underutilized. Say for example, it has a capacity of transmitting 100 megawatts, but because it is in parallel with other transmission lines and its impedance is high, it may not transmit exactly 100 megawatts of power. It will transmit small amount of power, say 20 or 30 megawatts of power because of high impedance. So therefore it remains underutilized. And the other line, say line number 3, which has a reactance of X3. Suppose it has the smallest reactance among the 3 lines. So it will carry the maximum share of the power, and it may get overloaded in that case. Okay, suppose again it also has a capacity of transmitting 100 megawatts of power, but its reactance is so small that instead of transmitting 100 megawatts, it's transmitting, say, for example, 150 megawatts. So therefore it gets overloaded and creates problems. The line may trip, and it will cause a large scale disturbance in the system. So therefore the power which is flowing over the lines is decided by the impedances of the lines. And in this connection, some of the lines may be underutilized and some of the lines may get overloaded. So therefore, we want the control over flow of power. Is it possible to have control over flow of power so that none of the lines is underutilized and none of the lines is overloaded? Answer is no. Simple. In AC power transmission, no, we cannot have control over flow of power. Yes, those of you, again, I quite often repeat these facts because those of you who have done this course with me, facts in your first semester, they have seen that with the help of facts devices like STATCOM, SVC, shunt compensators or series compensators, we can have a perfect control over the flow of power over different transmission lines. By using a facts device, we actually are able to change the impedances of the lines. Okay. For example, you can add some capacitance in series with a line. You can add some reactance in series with some other line, and you can adjust the impedances of the lines with the help of these facts controllers in such a way that they take equal share of power, and none of the lines is overloaded and none of the lines is underutilized. But the use of facts device, it's a very costly affair. Okay. Facts controllers are very costly devices. So therefore, to overcome this problem, we shift to HVDC power transmission. Instead of AC power transmission, we go to DC power transmission. And one of the main advantages of HVDC power transmission system is that we can have a perfect control over the flow of power. Okay. So therefore, if you have 3 or 4 parallel transmission lines, you can make the sharing of power among those lines, in such a way that none of the lines is underloaded, underutilized, and none of the lines is overloaded. So it is possible in case of HVDC power transmission system. It is an inherent characteristic or inherent advantage with HVDC power transmission system. This is not possible with AC power transmission system without the facts controllers. Here in HVDC power transmission system, you can have a perfect control over the flow of power, and you don't need any extra components, like you don't need facts controllers. So therefore, one of the main advantages of HVDC power transmission is that it is possible to have complete control over the flow of power over various HVDC transmission lines. So that's what I have written here. Power flow control is possible, which is not possible with AC transmission. So this was the 4th advantage. What next? Next is no Ferranti effect. No Ferranti effect. You must be knowing about Ferranti effect. During the lightly loaded conditions of a transmission line, your receiving end voltage becomes greater than sending end voltage because your system becomes capacitive in nature. And with capacitive nature of the system, your receiving end voltage always is greater than sending end voltage. You can explain it with the help of phasor diagrams, and you must have learned it in your power systems course. So this problem is not there with DC transmission, HVDC transmission. There is no Ferranti effect in HVDC transmission because there is no concept of capacitance in HVDC power transmission system. So Ferranti effect is absent in HVDC power transmission system. That means even if your transmission line is lightly loaded, you will never have your receiving end voltage becoming more than sending end voltage. And the problem is that if your receiving end voltage is more than sending end voltage, it keeps your equipments, load equipments, at risk, because a very high voltage may get impressed across the load equipments and they may get damaged. This problem is not there in HVDC power transmission system. There is no Ferranti effect. Okay. Next is low, no skin effect. No skin effect. Again, you must be knowing about skin effect. Because of the skin effect, the current gets confined to the periphery of the conductor, and it increases the overall or effective resistance of line, and copper losses increase. And this skin effect is absent in HVDC power transmission system. And in HVDC power transmission system, if this is the diameter of the conductor, the current, say, if this is the diameter of the conductor, cross section of the conductor, the current is uniformly distributed throughout the cross section of the conductor, and therefore there is no skin effect. So skin effect is absent in HVDC power transmission system. So next is low corona loss and less radio frequency interference. Low corona loss and less radio frequency interference. Again, the scary word corona. All of us are, scared of this word corona. Okay, coronavirus. But here, this corona loss, what this is. It is different, and it is in our control. Whereas coronavirus is yet to be under our control. Okay, this corona effect, electrical engineers have already brought it under control many decades back. So we know that this corona loss is directly proportional to F plus 25, where F is the system frequency. In HVDC power transmission system, frequency is 0, because DC means 0 frequency, right? So therefore, corona loss is very, very less in HVDC transmission system. Okay, let us hope coronavirus also becomes under our control, under the control of our medical team, medical practitioners, our doctors. So we have already controlled corona loss in electrical engineering, and I hope we will very soon become victorious in controlling the coronavirus. Okay, so this is next advantage. What is the next advantage of HVDC power transmission over AC power transmission? Next is simpler, less space required. This is very important. When you are transmitting power over AC transmission line or over DC transmission line, you need very long transmission lines, and those transmission lines are supported on the transmission towers. Okay, and those are very, very big transmission towers, each tower costing in lakhs of rupees. Very big transmission towers, very high, very broad transmission towers, and then there are strings of insulators, and on those insulators you support your transmission lines. See, it's very interesting. So let us suppose we have 400 kV AC transmission line, 400 kV, kilovolts AC transmission line. You want to design the insulator. What should be the voltage rating of the insulator? Should it be 400 kV or more? Since we are not having physical interaction, I'm not having physical interaction with you, it's a virtual class. So I'm not expecting any answer from your side. Let me answer it myself. So in this case, the insulator has to be designed for 400 into under root 2. 400 kV, it's AC, this is the RMS value. And what will be the peak? You have to design your insulator not against the, not for the RMS value of voltage. You have to design the insulator for peak value of voltage. And peak value of voltage means you have to multiply it by root 2. So therefore, the insulators of the transmission lines have to be designed for root 2 times 400 kV. On the other hand, if you are transmitting power over DC transmission line, and again, voltage of the line is 400 kV. Okay, in this case, you don't need it. You don't need to multiply it by root 2. You have to design your insulator for 400 kV. Whereas for AC transmission system, You have to design your insulator for √2 times 400 kV. So therefore, the size of insulator in HVDC transmission is less than the size of insulator in AC transmission. And the tower is also smaller in, see, this is the transmission tower. This is just a schematic, and these are the insulators. Okay, the height, the width, and the length of the cross arms on which you are hanging your insulators, it's small, because your insulators you have to design your insulators for 400 kV or for X kV, not for √2 times X kV. So that decreases the spacing required between the cross arms, and that decreases the overall size of the power transmission tower. So if you happen to see this HVDC transmission tower and compare it with the size of AC transmission tower, HVDC power transmission tower is smaller in size than AC transmission tower. That's what I have written here. Less space is required for HVDC transmission system. So this was the 8th point, which goes in favor of HVDC transmission system. 9th is simpler line construction. Simpler line construction. The line construction is, transmission line construction is simpler in HVDC than in AC. Next is ground can be used temporarily as return path. Temporarily as a return path. So, for example, in AC transmission system, how many lines do you require? 3 lines, 3-phase transmission. In DC transmission, you need only 2 lines, one positive, one negative. Okay. So sometimes if there is a fault with one of the poles, we call these lines as poles. If one of the poles is dysfunctional because of fault, you can use ground as a return path temporarily for some time till the fault is rectified. So this is another advantage with HVDC power transmission system. You need only 2 conductors, and in the event of fault on one of the poles, you can use ground as a return path. Okay. Next is fast fault clearing. Fast fault clearing time. If a fault occurs on an AC transmission system, what are the devices which clear the fault? Protective devices like protective relays, circuit breakers. It takes time for protective device like relay to sense the abnormal current and then give signal to the circuit breaker, and circuit breaker then trips and disconnects the faulty line from the healthy system. Whereas in HVDC power transmission system, we don't have any circuit breakers. It is completely electronic control. We are using thyristor converters. And with the help of these thyristor converters, these converters are electronically controlled, not electromechanically. So the fault clearance is very, very fast. Okay, another advantage. Next is no transmission of power to the fault. Let me explain it with the help of a simple diagram. This is a bus, and to this bus various lines are connected. Say these are line number 1, line number 2, line number 3, and on this side we have another line, line number 4, and then we have HVDC transmission, another line which is here. And suppose the fault occurs here. F stands for fault. Because of the fault occurring on the bus somewhere here, all these AC systems will contribute to the flow of short circuit current or fault or power to the fault, except this HVDC transmission system, because HVDC transmission system is electronically controlled. Whenever your controller there senses that the magnitude of current has increased, it takes care of that. It adjusts the firing angle or delay angle of your converters at converting stations, and it limits the magnitude of fault current. And in the worst case, it may make alpha equal to 180 degrees, for which converter output becomes 0, and therefore there is no transmission of power to the point of fault. The HVDC transmission line does not contribute anything to the power at the point of fault, whereas AC transmission lines for some time they may contribute to the flow of power to the point of fault. This is another advantage of HVDC transmission over AC transmission. This was point number or advantage number 12. What is the next advantage? 13. Asynchronous operation. Asynchronous operation. This is again a very important point. Asynchronous operation, you must have studied about synchronization of various alternators or synchronization of transmission lines. At a grid substation, the various transmission lines are synchronized together. They are synchronized in terms of phase sequence. They are also synchronized in terms of the frequency. When various systems are connected together, say 50 hertz systems, all systems must be at same frequency, 50 hertz, or all systems should be at same frequency, say 60 hertz. Is it possible to synchronize a 50 hertz system with a 60 hertz system? Answer is no. We cannot synchronize a 50 hertz system with a 60 hertz system. However, with the help of HVDC power transmission system, we can synchronize two systems of different frequencies. As I have told you in the very first lecture, in Japan, part of the country uses 50 hertz and other part of the country uses 60 hertz as operating frequency. And there it is possible to synchronize the 50 hertz grid with the 60 hertz grid using the HVDC link. Because HVDC means a DC line, and DC line there is nothing like frequency. Frequency concept does not exist there. F is equal to 0 in DC. So therefore, with the help of HVDC power transmission system, it is possible for us to synchronize two lines or more than two lines or more than two systems which are operating at different frequencies. This is called asynchronous operation. So this is next advantage of HVDC power transmission system. Next is more power per conductor. More power per conductor. I have already told you that in AC transmission there is the limitation because of the stability, and line reactance puts a limitation over the amount of power that can be transmitted over the line, and you can never load the transmission line up to its thermal limit. That is not the case with HVDC power transmission system. Length is not a constraint and stability issue is not there. Therefore, you can load the DC transmission line to its maximum limit, which is called the thermal limit. So therefore, if you compare a DC transmission line with AC transmission line, in case of DC transmission line, the power per conductor is quite high than in AC transmission line. This is yet another significant advantage of HVDC power transmission over AC power transmission. Okay. So finally, the last advantage which I am going to discuss with you is that there is no charging current in DC transmission lines. No charging current. Charging current is because of the capacitance occurring between the line and the ground, or because of the capacitance occurring between the conductors, between the lines. In DC, the capacitance is absent. There is capacitive reactance is infinite, or capacitance is absent. In AC, let us suppose we go for underground transmission. In case of AC, the long underground cables are laid under the ground and at very high voltage. Then since in the cable the conductors are very close to each other and they are buried under the ground, and the conductors are very, very close to each other, and the conductors are operating at very high voltage, a large capacitance occurs between the conductors at 50 hertz, and that causes the flow of huge amount of charging current between the conductors in the underground cable. And the magnitude of charging current means charging current is the current, it is basically the capacitive current, and it is at 90 degrees with respect to the voltage. And any current which is in quadrature with the voltage, it means what power? It means reactive power. So therefore, whenever a large charging current is flowing in the underground cables, that means only reactive power is flowing. And the magnitude of charging current may be so high that only reactive power may flow through the underground cables, and it will leave no room for the flow of active power. So you will not be able to make any active power to flow through underground high voltage AC cables. That's why we never go for underground power transmission. Otherwise, underground power transmission was one of the best choices for us. In AC transmission, you need transmission towers have to be erected. Okay, so say over a distance of 100 kilometers, if you want to transmit the power, hundreds of transmission